Hi, in this chapter we are going to talk about heap data structure. So let's get started. What are heaps? It is a binary tree. It is not a binary search tree, but it is a binary tree. And in a maximum heap, there are two main types of binary heaps: the maximum heap and the minimum heap. In a maximum heap, the keys of parent nodes are always greater than or equal to those of the children, and the highest key is in the root node. If you may recall, for a binary search tree, the largest node was the rightmost element. The smallest node was the leftmost element, because the parent has a smaller left child and a greater right child. Here, in a heap, the parent is always greater than its children, if it is a maximum heap, and if it is a minimum heap, a min heap, quite on the contrary, the parent node is always smaller than its children. So the lowest key is always in the root. And why is it good? Because there may be some situations when we have a set of data and we want to get the minimum or the maximum element very fast. For a binary search tree, it takes logarithmic time complexity, but with the help of the heaps we can do it ordo 1 or constant time complexity, and it has of course several applications, such as the Dijkstra's shortest path algorithm or Prim's algorithm concerning finding minimum spanning trees. So heap data structures are very important. And the second property is that it is complete. It cannot be unbalanced. We insert every new item to the next available place. So the heap is one maximally efficient implementation of an abstract data type called a priority queue. It doesn't matter, it's an abstract computer science stuff. And it has nothing to do with the pool of memory from which dynamic allocated memory is allocated. Okay. So there are two main heap properties. First, that it is complete. We construct it from left to right across each row. And of course, the last row may not be completely full. So for example, we have a heap already constructed like this, and we want to insert the next node. We have to do it to this way. Then we want to insert another one. We are not able to insert it to the right, the rightmost element, because it violates the heap property. We have to fill each row sequentially. So the next item would be here, then the next one would be there, then the next one would be there. So we keep constructing our heap row by row sequentially from left to right. This is the first and most important heap property. And the next one, of course, the key of the parent must be larger or smaller than its children's keys. This is it has to be larger if it is a max heap. It has to be smaller than if it's a min heap. We are going to implement the max heap, so that's why I'm going to talk about it as a heap in the coming videos. So yeah, we are going to implement the max heap, so the parent nodes are always greater than its children. So this is not a binary heap, and why? Because we have to fill each row from left to right sequentially, and here we have inserted the 20 to the rightmost element, and it violates the heap property. We should have inserted this node to the left child of node 3, so this is not a binary heap. But here, this is a binary heap. First of all, because it is balanced, and secondly, it is a maximum heap because each of the parent node is greater than its children. Why is it good? Because we know that the root node in this situation will be the greatest element of our data set. And if we want to get the maximum element from our data set, we just have to get this root node, and it can be done very fast. We can assign indices to each of these nodes, and we usually assign 0 to the root node and 1 to the left node of the root. The right node of the right child of the root will be the index 2, and so on. Why is it good? Because we can represent the heap with the help of an array like this. And it's completely self-consistent, because if we want to get the maximum item, we know that we have to get the item with the index 0, and from an array we can get an item with the half of an index in constant time complexity, which is very fast. And of course, if we want to get we want to make an algorithm, we have to make sure that if we have the ith node, we can find out its left and right child. And if we have the node I, the 2 times I plus 1 will be the left child, the 2 times I plus 2 will be the right child in this array. So we can represent this heap tree structure with the help of an one-dimensional array. Okay, so for an example, we want to build the maximum heap. We want to insert 23, it will be the first node. Then we want to insert 5, because we have to construct the heap row by row from left to right. That's why it's going to be the left child of 23. And we have to check whether we violate the heap property, and we don't, because 23 is greater than 5. And the second heap property tells us that the parent node will have to be larger than its children. So it's good. We have to insert the 100, and we have to go from left to right sequentially, row by row, so it's going to be the right child of the root. And we have to check whether we violate the heap property, and we violate it. Why? Because the 100 is greater than the 23. And we come to the conclusion that in a maximum heap, each parent node has the highest value. So we have to swap them accordingly. And now it is a heap. We have to insert 2. We have to go from left to right sequentially, row by row, so it's going to insert it to the left child of the node 5. And we have to check whether we violate the heap property, the second heap property. And we do not violate it, because the 2 is less than the 5, it is okay. We insert 210. We go from left to right, row by row, and that's why it's going to be the right child of the 5. But we have to make sure that we met the second heap property, so all the parent node has a greater value than its children. And it's not true, because 210 is greater than its parent 5. So we have to swap them. And then we have to call this method recursively. This fix up, we are going to call it the fix up method to check whether our heap is okay or not. We have to swap them because the parent node must be greater than its children. And now the greatest element is at the root node again, so it is a good maximum heap. What about the heap sort? We have been talking about how to construct a heap. Okay, but we can construct the sorting algorithm, which is very efficient. That's what we call the heap sort. It is a comparison-based sorting algorithm. We use a heap data structure rather than a linear time search to find the maximum. And although somewhat slower in practice on most machines than a well-implemented quicksort or merge sort is better, it has the advantage of a more favorable worst case O(n) log n. The worst case scenario for quicksort is O(n), which is linear time complexity, very, very slow. Heap sort is an in-place algorithm, which means that it doesn't need additional memory, very, very efficient. But it's not a stable sort. So we keep swapping the root with the last element plus maintain the heap properties. So we swap with the last node. So we swap 210 with 5. Consider it 210 sorted, and it's very important that from now on this node is no longer part of our tree we want to sort. So until now we have 5 nodes, but here we consider this node sorted, this 2210, so we consider it sorted. It is not anymore part of the tree. So we have only 4 nodes from now on. So then we have to make sure that the root is the maximum, so we do not violate the heap property, so we have to swap these items accordingly. And then we have to swap with the next last node, and because we have considered 210 sorted, the last item will be 2. We have to swap them. we consider the 100 sorted, so it doesn't belong to the tree anymore. We have only 3 nodes left. And we have to reconstruct the tree in order to maintain the heap properties, so we have to swap 23 with 2. And now the greatest element is at the root. Now we have to swap the 23, so the root node, with the last item, which is 2, and consider it sorted. 23 has already been sorted, so it doesn't belong to the tree anymore. We have to make sure that we have only 2 items, the 2 and its left child 5. It's not a heap because the parent must be greater, so we have to swap them. We have to swap them. So the 5 will be the root node. We have to swap the root node with the last item, and because there are only 2 items, it's straightforward. And we consider the 5 sorted. And then we have only a single last element, so we consider it sorted. And we have get the numerical ordering: 210, 100, 23, 5, and 2. So we have sorted our elements, and if you see, we do not need any additional memory. We just have to we represent this heap with the help of arrays. We just have to swap the numbers in this array. It's a very, very efficient sorting algorithm. What's the problem with it? That first we have to construct our heap. Until now we have talking about binary heaps, but there are several other types of heaps, such as the binomial heap or the Fibonacci heap. Binomial heap is similar to a binary heap, but also supports quick merging of 2 heaps. So it is important as an implementation of 2 mergeable heap abstract data type, the so-called multiple heap, which is a priority queue supporting merge operation. A binomial heap is implemented as a collection of binary trees, so we have more binary trees, not just a single tree-like structure, and we keep merging them accordingly. I think binary heaps are much more important, so I just want to talk a bit more about this too. Insertion O log n time complexity can be reduced to constant time complexity with the help of binomial heaps. Because if we insert some elements, we have to reconstruct the trees to be able to make sure the heap properties are met in binary heaps, as we have discussed. And reconstructing the trees may take logarithmic time complexity. But with the help of binomial heaps, we can do it in constant time complexity. So it's a bit more faster, but it's much more complex. And the Fibonacci heap, it is faster than the classic binary heap. The Dijkstra's shortest path algorithm and Prim's spanning tree algorithm run faster if they rely on Fibonacci heap instead of binary heaps. But it's very hard to implement efficiently, so usually doesn't worth the effort. Unlike binary heaps, it can have several children. The number of children are usually kept low, so in a binary heap, each of the parent node has a left and a right child. But in a Fibonacci heap, it can have several children. So we can achieve order 1, so constant time complexity insertion operation, instead of the logarithmic time. So it will be faster than our binary heap. Every node has degree at most O log n, and the size of a subtree rooted in a node of degree k is at least fk plus 2, where fk denotes the kth Fibonacci number. So that's why it calls the Fibonacci heap. It's very, very hard to implement it efficiently, and that's why we usually do not bother about it. It's good to know about that. Fibonacci heap is very efficient. So the last thing I want to talk about is the time complexities. For a binary heap, the binary heap is that we have considering and we are going to implement. The binomial heap is a bit better. The Fibonacci heap is very good, as you can see. We can do lots of operation in constant time complexity. The deletion is the only one that has logarithmic time complexity. Fibonacci heap is very, very efficient, but very, very complex, and that's why it's very, very hard to implement. But the binary heap, the find the minimum, find the maximum, we are considering now a minimum binary heap. It can be a maximum, then we can find a maximum in constant time complexity. But as you see, the logarithmic time complexity is very, very good in algorithmic theory. So we can do the deletion, the insertion, and decrease key operation with the help of binary heap in logarithmic time complexity. It is very, very efficient. So in the next videos, we are going to implement the binary heap together, the maximum binary heap together. Thanks for watching.